Hi everyone, hope you're keeping well. We're going to have a look at the week 2 homework question. This is the ordinary level one. It's from the 2023 paper. It's question 7. So another mechanics based question, which is where we're keeping the focus on for now for these revision questions. Just a quick note, before you try these, make sure you've gone through the notes that I gave you ahead of time and maybe watch the video from the previous week and this one before tackling the next one. It'll give you a better place to start from, just to jog your memory a little bit. So make sure you skim over the revision notes and then have a look at these videos. So let's get cracking on week 2. Okay, so a big drop is an amusement ride. I should say as well, have the hard copy of this question with you. Will make this a lot easier to follow. So the actual question sheet I gave you. A big drop is an amusement ride where a carriage with passengers is lifted to the top of a large vertical tower and then released to fall down the tower before it breaks and comes to rest. Okay, what are we being asked? Part 1. As the carriage travels to the top, the carriage is gaining potential energy. What is meant by potential energy? Now, a lot of people said that it's energy that is kind of stored in something. Energy stored in a body, which is partially true. But it's down to where it is in a force field, due to its position in a force field. Now, I'll say let's go into that in a little bit more detail in a moment. Due to its position in a force field. You have to be detailed to get the full whack of marks here. So when we say force field, usually we're talking about the gravitational field. But we could equally be talking about electric or magnetic or anything else. But usually we're talking about gravitational potential energy. And what that means is where you are based on your height. So if an object, let's say that's the ground, these two objects, this one has more gravitational potential energy than this one because it's just up higher. Because the formula for gravitational potential is mass times the acceleration due to gravity times h. Now, a quick note as well, guys, you don't have to memorize all this stuff. You probably will know it by the end, but remember, these are all in your logbooks. You don't have to memorize these, just have to find them quickly on the day. So the more practice you do with the logbooks, the quicker that process will be. Okay, that wasn't really necessary for that. It's just an explanation. Part 2. Draw a diagram of the forces acting on the carriage as it travels up the tower at a constant velocity. Okay, well, down to Newton's laws of motion. If it's moving at a constant velocity, that means that the carriage is the forces acting on it are balanced. So you have its weight, and you have the force from the ride itself. So the force from the machine, we'll call it. And try and draw these arrows roughly the same length to indicate that they're the same. They're balanced. You know, however many newtons you have going down because of weight, it's balanced by the upward force from the machine because it's moving at a constant velocity. Okay, part 3. The carriage is dropped from a height of 37 meters above the braking zone. The mass of the carriage is 6,200 kgs. Calculate the potential energy the carriage had before it was dropped. Okay, so if it's dropped a height of 37 meters, and it has, let's see what we've got. We've got the height is 37 meters. The acceleration due to gravity is 9.8 meters per second squared. And the mass of the carriage is 6,200 kgs. Now, they've already given us the right units. We don't have to look out for traps here. We just have to use the right formula, which is that gravitational potential one, which is n times g times h. So it's the 6,200 times the 9.8 times the 37. And let's see, let's not be lazy. Let's actually do it rather than look at the mark scheme. 6,200 times 9.8 times 37 equals... So our answer, and we'll come to units in a moment, is 2248120. And because it's energy, your unit's always going to be joules for energy. Okay, and that's part 3. Let me just check if that's still visible on the screen. It is, okay. Okay, part 4. What is the main energy conversion that takes place as the carriage falls? Well, the gravitational potential that it had due to its position is converted into kinetic energy. So gravitational potential into kinetic energy. Straightforward enough. As it loses gravitational potential energy, it's moving more, it's moving faster. So the loss in gravitational potential is equal to the gain in kinetic. Calculate the velocity of the carriage when it has fallen 37 meters. Okay, so a couple of ways you could try this. You could use the Suvat approach. Okay, now I wouldn't suggest it for this because this isn't the best option, but it will work. If you think about the carriage, when it starts at rest, you have u is 0 meters per second, and it's going to be accelerated by gravity with 9.8 meters per second squared of acceleration, ms minus 2 even. Sorry, my brain just malfunctioned there a little bit again. We know the displacement was 37 meters, and we don't know what the final velocity was, and we don't know what the time was. What we do want to get is the velocity. So we're looking for v here. So we have v equals u plus at, s equals ut plus half at squared, and v squared equals u squared plus 2as. There's the equations of motion. So we're looking for one that has the 3 we're looking for and the 4th we're not. Sorry, very sorry guys, my brain is very tired, it's late in the day. The 3 things we have and the one we're looking for. So something that has an S, U, an A, and a V. So probably this guy here might be the winner. Yeah, let's go for this here. So v squared is equal to u squared plus 2as. Now its initial velocity was 0, so that's just going to go away. So we've got v squared is equal to 2 times 9.8 times 37. Okay, which is 725.2. And remember, that's the square of the velocity. So let's just get the square root of our answer. And we have a velocity of 26.9 meters per second. And that's a viable approach, okay? That will work. That's if you like SUVAT, that'll do the job. But there's a way easier way of doing it. And that's equating the loss of one type of energy with the gain of another. So here, what's happening is as the pod falls, or the carriage, whatever it's called, it loses gravitational energy, but that is gained as kinetic. So the loss in gravitational potential energy is equal to the gain in kinetic. So for this, the gravitational potential is mgh, like we talked about before. That's going to be equal to, and for kinetic energy, the formula is half m v squared. Now, the mass is on both sides. Cancel it off. It doesn't matter the mass of the object. So we have g times h is equal to half v squared. Let's just get rid of this half and bring 2 across. We have 2 times g times h is equal to v squared. And if you look, that's essentially what we had up here. 2 times g times h. So that's 2 times 9.8 times 37 is equal to v squared. And we've already done that, but let's just do it again for the crack. 2 times 9.8 times 37, depending on your definition of crack. And that's the 725 again. Square root of the answer. Boom. There's your 26.9 meters per second, okay? Excuse me, whichever method you prefer to use for that, I'd suggest this is probably a bit easier, the energy conversion, but whichever floats your particular boat, you do you. Okay, so that is part V, 2 approaches to V. VI, calculate the time it takes to fall 37 meters. Okay, this probably would be a SUVAT again, so let's just SUVAT. We have our 37 meter drop, acceleration of 9.8 meters per second squared. Initial velocity was 0. And now we know that the final velocity is 26.9 meters per second. So there's all the information we have, and we're looking for t. So I think any of the, let's just write out the formula. Anything that has a t in it is going to be good, but some are going to be more useful than others. So v equals, sorry guys, I can only say I'm tired so many times, but so mistakes happen. V equals u plus at, s equals ut plus half at squared, and v squared equals u squared plus 2as. And remember, you don't have to pull these out of your hat. You can have them on the log tables. It's just I'm kind of familiar enough with them. Okay, so we're looking for t, so we're looking for any one of these that has a t in it. Now that would work, but it's going to be very complicated. This one's nice and straightforward. V equals u plus at. Well, u is 0 again, so v is equal to at. And we're looking for t, so just divide both sides by a. I'll bring the a across, whichever you prefer saying. V over a is equal to t, so we have our 26.9 meters per second divided by 9.8 meters per second squared. Will give us our time it takes. Divided by 26.9 equals. No, I've done it backwards, haven't I? 26.9 divided by 9.8. That's 2.744 seconds. Okay, that's part VI. Let me just make sure I'm not giving you false information here. Just check that that's correct. Excuse me. Yeah, 2.75 seconds, 2.74. Okay, that's grand. Last little stretch here. So that's VI. VII. Captain. Draw a diagram of the forces acting on the carriage as it falls. Okay, well, as it's falling, the only force acting on it really is weight, pulling it downward. It's weight. There will be some air resistance upwards, but it's going to be nothing compared to the force due to gravity. So let's just label them. Air resistance, weight, and that's VII. Make sure that this arrow is bigger than that one because it's accelerating downward. And finally, draw a velocity time graph for the motion of the carriage from when it was dropped to when it comes to rest. Okay, so velocity time graph. Let's flip this over for a minute. So time on the x-axis, velocity on the y. So it starts off at 0 because it was stationary. Then it's going to get faster, faster, faster. It increases its velocity until it stops. So it's literally going to be that. Do we have to put some numbers on this? Axis labeled, acceleration shown, deceleration zone. Okay, yeah. Velocity increasing, because then velocity has to come to 0. So then it's going to slow down. So it's going to accelerate a lot, and then it's going to slow down on the braking. So we have our acceleration due to gravity, and then when the brakes kick in, it's like a cushion of air or something to slow it down so you don't slam into the ground to slow you down. Okay, I don't think they're looking for any units, but let's put them on because we should. So it's meters per second over seconds. But you don't have to put any, I mean, we figured out the time was 2.74 seconds from it being dropped. But that's fine to me. Alright guys, hopefully that was useful. Again, the key take home from this one would be to sometimes equating the types of energy is the way to go. Loss of one type of energy is the gain in another. It can save a bit of heartache when it comes to suit that. But hopefully that was useful to you. And as I say, have a gander over the notes and maybe at the video for last week as well before trying this week's homework question. Okay, take care and have a good one.